All right, hey algebra, it is our first official Algebra 1 lesson. You'll see we're starting, it says lesson 1-1, operations with real numbers. So we're starting off with, in our algebra book, which looks like this. This is the cover. You maybe have seen it in our classroom when we were there. So when we get back to school, I know I'm sharing these with Miss BizDoc, so we'll see if I have enough for everyone. But eventually I'll share the e-copy and how you can get online and look at this too. All right. So we're starting off with chapter 1, which let's see if I can get to it here. Table of contents. So you can see right here, topic 1 or chapter 1 is solving equations and inequalities. And we are starting with 1-1, operations on real numbers. So let's go back to our note sheet. So I'm going to write in here. You guys should take notes in your notebooks. Why? Because every time we have a quiz or a test, you're going to be able to use your notebook. So the more examples you have in there, the better you'll be prepared. And it's also helpful when you're doing your work to have something to go back and look at. So first we need to talk about what an operation is. Well, hopefully you guys can think of operations. Those are like adding, subtracting, multiplying, dividing, exponents, square roots. Those are all operations, right? And we're going to talk about operations with real numbers. So real numbers is in contrast to imaginary numbers. You don't have to know about imaginary numbers yet. You won't learn about those until algebra 2. But we live in the world of real numbers. And there's also this whole set of imaginary numbers that you'll learn about later. So real numbers are like -5 or 2.897 or 1/2, right? Or 1 3/4. Those are all real numbers. So let's work through these examples together, okay? So in a set of numbers from 1 through 10, okay, I can think of all those numbers from 1 through 10, which elements are in both the subset of even numbers and the subset of multiples of 5. So it's basically asking us to think here. I make a text box. If I have these numbers, 1 through 10, this is the original set. Each of these numbers is considered an element, right? So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in this set. So now it's asking us which ones fall into the subset of even numbers, okay? Let's do another box here, even numbers. Well, which one of those are even numbers? If I look above, I know it's 2, 4, 6, 8, and 10, right? Those are the ones that are even from above. Okay, now let's get a new one and let's do multiples of 5. Multiples of 5. Well, that would be 5 and 10. Okay, so what it is asking us is in these two subsets, which means they are a partial set of the big set above, right? This one falls above it. Which numbers are in both of those subsets? It says both. Okay, well, I can look. Well, this is the shorter set, so I'll start here. 5 is in this one, but it's not in that one because it's not even. So that's not in both. 10 is a multiple of 5, but it's not even. So there's only one number that's in both subsets, and that's the number 10. So the point of this question is not that it's tricky, it's that you can understand what's being asked in the vocabulary word. And there's only one number in that subset that is both even, a multiple of 5, and falls between 1 and 10. That number is 10. Okay, now you guys try it. You can pause if you want to try it on your own. Then you can come back and check if you got it right. So which numbers in set A, so this set right here, are elements in both the subset of odd numbers and the subset of multiples of 3. So this is called set notation. This is saying set A equals all of these numbers in those squiggly brackets. So let's put some things in here. The first subset is odd number. So which one of those are odd? Well, 1, 3, 5, 7, and 9, right? And now instead of making a separate subset, I'm just going to go back and circle in here which ones are also multiples of 3. And 1 is not. 3 is a multiple of 3. 5 is not. 7 is not. And 9 is a multiple of 3. So there's only two numbers that are odd and multiples of 3 from this set, and that is 3 and 9. Okay, so that's my answer for that one. All right, for the next example, we need to quickly remember what this means. So this symbol, hopefully you can remember, you see that symbol, it means Square root, right? What is the square root of a number? So then we have to remember what square root means. So that means here it's saying the square root of 9. So it's asking you, what is a number that you can multiply by itself to get 9? Well, I know I can multiply 3. Sorry, I didn't mean to add that line right there. 3 times 3 will give me 9. That means the square root of 9 is 3. The reason it's called a square root is because you're basically saying I can make a square that has the sides 3 by 3, right? And the area of the whole thing is 9. So the square root or the dimensions of each side is 3. So what if I do the square root of 16? So I start thinking to myself, well, what number times itself gives me 16? Oh, well, I know 4 times 4 gives me 16, right? So I know the square root of 16 is 4. The square root is the opposite of squaring a number, right? Because if you wanted to write this, if you wanted to square a number, you would write 4 squared equals 16. So the square root is just going backwards. You're starting with a 16 and getting 4. Okay, so hopefully you can remember that because we're going to have to use it in these problems. The first example says Jim is playing a math game where he needs to put a set of 3 cards in numerical order. His cards show 40 over 11, square root of 324 over 36, and square root of 10. Order the cards from least to greatest. All right, so if I'm dealing with 40, I have to put these in order. Let's deal with 40 over 11. That is an improper fraction, right? So hopefully you remember how to turn it into a mixed number because that'll help me order it. So how many 11s are in 40? Well, there's 3. Let's take away 33. And then the remainder is then 7. So this is actually the mixed number 3 and 3/7. Hopefully you remember that. If not, you can see where I got it from is, oh, Miss Harrington made a mistake. I don't know why I wrote 3/7. The 3 is from up here, right? The top number. And then the numerator of the fraction is 7, your remainder. And the denominator is 11. I don't know why I wrote 3/7. I was looking at that. So 3, you can think about it. Here's the 3 and 7/11. The denominator shouldn't change from what it was. So I know this is 3 and 7/11. So now I'm thinking about that. 3 and 7/11. Well, I know that that's a little more than 3.5. Why? Because 7/11 is a little bit more than half. So I'm just going to take that note there. Okay, now let's look at this. This one's a little bit tricky. It says the square root of 324 over 36. You're like, Miss Harrington, that's way too complicated of a square root from the examples above. So here's what you can do. You can break that up into 324, the square root of 324, over the square root of 36. So I don't know what the square root of 324 is. I don't know what number times itself gives me 324, but I do know what number times itself will give me 36. Do you guys know what that is? Well, that's 6 times 6 gives me 36. So I know the bottom number is 6. Okay, and then for the top one, instead of guessing and checking, I'm going to use a quick calculator. So I suggest if you guys use the desmos.com/scientific calculator. So you can look up Desmos scientific calculator and it looks like this. So let's see, what is the square root of 324? Well, here it is, 18. So I'm going to go back. Now I know the top number is 18. Okay, well, what's 18 divided by 6? That's easy. I know that one. That's 3. All right, and then the last number I have to deal with is the square root of 10. There is no number I can multiply by itself, whole number, that's going to give me exactly 10, right? But here's what I know. I know the square root of 9 is 3, and that's 1 below it, right? Supposed to be an arrow. And then the next number I know is the square root of 16 is 4. So I know that that number is going to be what? It's going to be closer to 3 than it is to 4 because the square root of 10 is closer to square root of 9 than 16. So my initial guess is to order these from least to greatest is that square root of 10, since it's closer to this, is going to be really closer to the whole number 3, right? But it's going to be a little bit more than 3. So it's going to be maybe 3.1, 3.2. I'm not sure. But it's going to be a number a little bit bigger than 3. So I know the smallest one, let me get a different color here. The smallest one is definitely 3. So I'm going to put 3 first. The second largest one is going to be this one because I just figured out that it has to be just a little bit more than 3. So I'm going to write square root of 10. You always want to write the original numbers they gave you. And then the biggest number is going to be 40 over 11 because we said that's greater than 3.5. So that's the order I have. And just to check, let's see what the square root of 10 is. Let's clear this. Or new line, square root of 10. I bet you it's close to 3.1. Yeah, it's 3.16. So we were right. It's our check. Okay, so what we're really doing here is using our number sense to kind of figure out which numbers are larger and smaller. So now you guys try this one, pause and try it. And I'm going to work on it here, talk through it. After you're done, you can press play again and check. Okay, 0.25, I know what that is. Now let's deal with square root of 1 over 9. I know I can break that up as the square root of 1 over the square root of 9. What number times itself gives me 1? 1. 1 times 1 is 1. What number times itself gives me 9? 3. So that's just 1/3. And I also, just for fraction's sake, I'm going to write 1.25 as 1/4. That'll help me compare. So now I have 1/4 and 1/3. All right, what about 6 over 25? 6 over 25. Let me change my color. So what do I know about 6 over 25? Well, if I had 1/3 of 25, could we make all of these have the same denominator, 3, 25, and 4? Is there a factor that's the same? 75, 100, 3 times 4 is 12. I know, let's divide. I changed my mind. I'm going to leave this 0.25. 1/3, I know, just from memory, and if you don't believe me, you can check, is like 0.33333. So I already know that this number is bigger than 0.25. So what's 6 divided by 25? Do you guys remember how to do this? If you don't, you can use your calculator. It's fine. So I can put a point and a 0. And the first thing I'm thinking is, how many 25s are in 60? Well, that's 2. Take away 50, 10 left over. And then remember, I can add another 0 and bring it down. Now how many 25s are in 100? 4. And when I'm done, I don't have to keep going because that minus 100 comes out to 0. So now I just pull my decimal up, point. So I know 6 over 25 is 0.24. So that's the smallest one. So from least to greatest, 6 over 25, because that's 0.24. Then it's 0.25, because that's 0.25. Then the biggest one is square root of 1 over 9, because that came out to be 0.3333 repeating. I could put this bar over it. That's the repeating bar that tells you that 3 goes on forever. Okay, now that we've practiced some ordering, the last thing we're going to do is talk about different kinds of real numbers. Okay, so we talked about real numbers being all the numbers that you know right now. Every number you've learned is real. And then there's 2 kinds of real numbers. There's rational numbers, all these numbers in this yellow circle, and then there's irrational numbers, all these numbers in the purple circle. So rational numbers are the numbers that you guys are most familiar with. They're decimals and fractions that have an ending, right? So 2/3, 1/2, any of these decimals, 3.2125, right? And that doesn't mean it has to end when you can see it. It can end 1,000 digits out, 3.2125897. It has to have an ending though, right? It includes integers. Integers just means positive and negative numbers. So -3, -24, 0, 7, all of those are integers. And then it includes also natural numbers. Natural numbers are sometimes called counting numbers. So all those numbers you learned when you're in pre-K, 1 and up. So those are rational numbers. So you've worked with those, you know those. What you're adding to your vocabulary now are irrational numbers. So these are real numbers, they're still real, but you cannot write them as a finite fraction. That means they cannot end. The number doesn't end. So what do I mean is that if I did the square root of 3, so that is an irrational number. And let me show you why. Let me go to the calculator. If I do the square root of 3, so you can't see this here, but it is just, it doesn't end. It continues on and on. If you do it, I think Desmos is just cutting it off for me. But let's say, so you can see if I put it on my phone, it keeps going and going and going and going. It doesn't end because it's just, imagine a number where you would keep writing the decimals all day over and over and over, and you could die before you were done writing the last digit because the decimals keep going on forever. That's how you know it's irrational. Another common irrational number is pi. So that's that digit 3.14, right? And you have people who memorize it, but you can't ever memorize the whole number for pi because it never ends. It's kind of crazy to think of that. But irrational numbers don't end. They continue on forever. Or rational numbers can be written as a nice compact fraction because if they can be written as a fraction, they have an ending. Okay? All right. So now your task is going to be to use these definitions of rational versus irrational numbers. You're going to determine or discover some rules, which should be fun. All right. I'll see you next time. We stop recording. Bye, guys.